Yeah, very good morning to one and all. Welcome to the fourth day of World Nano Congress on Advanced Science and Technology. Today we have Dr. Adam Lee from RMIT University, Australia. It is my pleasure to introduce our speaker, Dr. Adam Lee. Professor Adam Lee is the Professor of Sustainable Chemistry in the School of Science at RMIT University. He has held chair appointments at the Cardiff, Warwick, Monash, and Aston University, in addition to the prestigious EPSRC Leadership Fellowship. His research addresses the rational design of functional materials for sustainable chemical process and energy production, and the development of in situ methods providing molecular insight into the surface reaction. He was awarded the 2000 C.R. Brent Prize by British Vacuum Council, the 2004 Fonda Fasella Prize for Prize of the Electra Synchrotron, and 2011 McBain Medal of the Royal Society of Chemistry and Royal Society of Chemical Industry, and in 2012 Bailey Medal of the Royal Society of Chemistry, the Society of Chemical Industry. With this short, brief bio, I'm inviting Dr. Adam Lee to deliver the talk. Over to Adam.
That's great. Thank you very much for the kind introduction, and thank you very much to the organizers for the opportunity to speak today about some of the research in our group. It's a great honor and privilege to be able to present our work. Hopefully it's not too early in the morning for everyone there. It's early afternoon here in Australia. And what I'll be talking about is our approaches to developing a new class of catalysts called spatially orthogonal catalysts. And I'll show you how they can be applied to some sustainable chemistry. Okay, so first thing I think is probably just to set the scene a bit on the importance of catalysis in modern day life. So hopefully most of you are aware that catalysts play a crucial role in the production of a vast array of different chemicals. The history of catalysis is long, roughly 150 years, and the original catalysts were developed for fuels production. So the refining of fossil fuels, coal and oil, to produce fuels on one side through cracking technologies, and our higher value, more complex molecules through reforming technology. Over the last 30 years or so, we've seen a big change following the ideas of sustainability in the way that we do catalysis, particularly regarding the feedstocks. There's been a big shift away from fossil fuels and towards the use of renewable resources, particularly biomass. And again, the idea here is to take these different feedstocks and make similar chemical products. So biorefineries take green chemistry and they apply it to biomass to develop fuels or to drive the production of, for example, fine or bulk chemicals. So we have to develop new catalytic and green technologies to allow us to do this. There's also a large drive at the moment around the world in developing catalytic technologies to harness the power of sunlight for transformations that, for example, produce solar fuels, such as hydrogen, or the production of chemicals such as methanol. So these changes away from fossil fuels to more renewable resources also need a change in the way we do catalysis. Traditional catalysis is conducted in the organic phase, often at high temperature, whereas biomass by nature is derived from materials that are rich in water. So we have a lot of aqueous phase transformations that need to occur at lower temperature. And underpinning all of these is, for example, the United Nations Sustainable Development Goals of 2030, where we're trying to achieve a reduction in the degree of hunger in the world. We're trying to improve the cleanness of our water supplies, to use alternative energies, to use resources more wisely, and of course to mitigate climate change and damage to the aquatic ecosystems. So I'm going to focus on a particular class of catalysts, which are multi-step catalysts, which drive a process called a cascade. So the idea of a cascade is very simple. We can have a reaction where we start with one molecule and we use a catalyst to drive a transformation to make a single product. And then we can use either the same catalyst or a different catalyst to drive a second transformation to form another product. So it's a cascade. We have multi-step reactions in here. And the advantages are many of doing this sort of approach. If you can drive reactions in one reaction vessel, you can improve the atom economy. In other words, more molecules that you start with end up in the final product. We can thereby minimize the amount of waste, and we can improve the overall efficiency of the process. This sort of cascade also allows us to do reactions with a product here that you, for example, cannot buy. So some molecules you cannot purchase from a company. They are intermediates that are very unstable, and so you can't normally do transformations with them. We can make these molecules in situ by starting with a stable molecule over here. We produce this product, and then we transform it within the same reaction vessel. So it allows us to use intermediate molecules that we can't actually isolate normally. A couple of examples here. First of all, of a reduction and then an oxidative coupling of, in this case, nitrobenzene. And here's an example where catalyst A and B are the same. Both are gold titania. And so this catalyst in one reaction vessel can do a reduction using hydrogen and then an oxidative coupling using oxygen to make our coupled product here. This is an example which is easy because it's the same catalyst, but is also potentially dangerous because you have a high pressure of hydrogen and you have to purge that very carefully from the reactor before you introduce oxygen to avoid an explosion. You can have reactions that are cascades that involve acid and base chemistry. Here's an example of a biomass molecule, glucose, which we can transform over a hydrotalcite, HT, that's a solid base catalyst, and then drive the second step over a solid acid catalyst, for example, amberlist and acid resin. So here, for example, we can do an isomerization of glucose to fructose using our base catalyst, and then a dehydration to make a molecule called hydroxymethylfurfural over an acid catalyst. So two different types of catalyst in one reaction vessel. And I say these are very advantageous for doing multi-step reactions. However, getting the right kinds of catalysts and getting them to work together is very difficult. So historically, there are very few examples of these cascades using heterogeneously catalyzed liquid reactions. Here is one example of a cascade which involves polyalcohols. So some sugar molecules here, sorbitol, in which we start with a biomass stream of these polyalcohols. We use one catalyst in one reactor to start the transformation. And then we have a set of additional catalysts, all in different reactors, that eventually can give us a biofuel. Key point about this is that we have multiple different catalysts, but all in different reaction vessels. So this is not an example of a one-pot reaction. We have to separate and purify each of these species at each step along the way, and that introduces waste and inefficiencies. The ideal kind of multi-step reaction is a one-pot cascade. These are very rare. And traditionally, to make the catalyst, you have quite complex sets of synthesis, many steps in the chemical synthesis, often with difficult to handle reagents like ozone, UV light. So we have complex syntheses to achieve these, or the catalysts themselves incorporate organic functions. You can actually see this here. This is an organic acid, a sulfonic acid. And because we're using organic functions in many of these, they offer poor thermal stability. We can't heat the catalyst to high temperature because they decompose. And we also often have low active site density. We only have very few of these acid groups in our catalysts, so our activity is low. Or you can turn to polymers and you can try and make polymeric multifunctional catalysts. So the red and the blue strands here have different catalytic functions, but as you can see, they're all mixed in together. We don't have very good control over the reaction sequence of doing this. And so there's a need to try and make better catalyst systems for cascades. I'm going to show you some examples, first of all, from oxidation hydrogenation reactions. And these are an important class of reactions which underpin sustainable chemistry. So you could, for example, take naturally occurring alcohols, for example, cinnamon alcohol that you obtain from the cinnamon leaves, and you could transform those using, for example, a platinum or palladium catalyst to the corresponding cinnamaldehyde, which is important in fragrances and in flavoring applications. And you can even oxidize it further to make the corresponding cinnamic acid, which is a precursor to aspartame, so an artificial sweetener. And in general, of course, reactions that you can do by oxidation, the same catalysts are often effective at doing the corresponding reductions. So we'd like to try and make these cascade reactions using oxidation and hydrogenation catalysts, which will allow us to take biomass and produce a range of important chemicals and fuels from them. I'm going to first of all show you a single step of a cascade reaction using a palladium catalyst. So palladium has been known for a long time that it's very active and selective for alcohol oxidations. That's the first step in a cascade. And my group has spent a long time, over a decade, working to try to identify the active catalyst species that's involved in driving the transformation of an alcohol. You can see here through to the corresponding aldehyde group, the unsaturated group. And you ideally want to do that without touching the double bond. So if you look carefully, there's actually a double bond here, a CC double bond, and you don't want to attack that during the reaction. So what we've shown is the active site responsible for these transformations is actually a metal oxide, palladium oxide. So small palladium oxide nanoparticles are very active for these transformations. And as the catalytic reaction proceeds, the catalyst becomes reduced and it makes large metallic particles, which have a very low background rate. So palladium oxide is good and palladium metal is quite bad for this chemistry. I'm just showing you here some results of some XAFs, so some X-ray absorption measurements in situ, where we can track the degree of the alcohol conversion as a function of the oxidation state. And what you can see is that palladium oxide, high oxidation state, is very good for this catalyst, for this catalytic transformation. So palladium is great for alcohols to aldehydes. What it cannot do is oxidize aldehydes to acids. So we can do step 1 of our cascade, but not step 2. However, it turns out that platinum is very active for aldehyde oxidations, step 2. So we've done a lot of work again trying to identify the active site responsible. It turns out it's also a metal oxide. So PtO2 is very good at aldehyde oxidations, just showing this here. So if you give a platinum catalyst aldehyde, it converts it very effectively through to the corresponding acid. So this is a selective oxidation, taking the aldehyde group to a carboxylic acid, and it doesn't touch the double bond. So platinum is great for step 2 of a cascade reaction. However, if you show platinum the starting material, an alcohol, nearly all of the alcohol, or a fair fraction of it, actually ends up going down this pathway, the black numbers, going up towards styrene. It undergoes completely different chemistry, actually a decarbonylation to an undesired product. So we have two metals, palladium that's very good for this transformation, and platinum that's very good for this transformation. But it can't see the first alcohol, otherwise it poisons the catalyst. So the question then becomes, how do we couple together, how do we combine two different types of catalyst? Traditionally, we would simply take a physical mixture. We would take two individual catalysts and put them into the same reaction flask. Or we would take a catalyst support and we would randomly put these two elements into the catalyst. So we're not controlling the location of those. That's a problem. So for example, if we do those approaches, then we have to face the reality that the reactant molecule could go to the wrong active site first in a cascade. If it does that, the best case scenario is it simply bounces back in a wasted encounter. The worst case scenario is it could poison the catalyst or it could make the wrong molecule. So we need a way to control the sequence in which reactant molecules can interact with different active sites. What we'd like is that reactant molecule in our bifunctional catalyst to find active site 1 and to make product 1, and for that to then go to a second active site and make final product 2. So that's first question. How do we control a reactant molecule and steer it, direct it to go down this pathway, but not this pathway? The other thing we have to think about, particularly for acid-base catalysis, is how do we stop active sites interacting with each other? If you have an acid catalyst and a base catalyst, we know if they interact with each other, they could neutralize. So we need a way to do that. And our solution has been to turn to porous materials, specifically hierarchically porous materials, where we can take a macropore, that can be a well-defined macropore, in which we can functionalize with one active site, such that the reactant undergoes a transformation in this first area here to make product 1. And that product can then diffuse into much smaller mesopores, which you can see here. So product 1 goes into mesopores where there's a different active site, and it can then make a second product. So in this approach, we're using the pore hierarchy, the fact we have active sites spatially separated, as you can see here, to control the reaction sequence. So the goal, what we're trying to achieve, is controlling the reaction sequence and preventing different catalyst functions from interacting with each other. How have we done that? Well, we've taken a templating approach to achieve this, and I'm showing you now the synthesis of these templated materials. We start off with a material that has two types of template: a colloidal nanosphere, that could be polystyrene, that's a large macropore template, and then we have a mesoporous array, which contains a smaller surfactant template, for example, P123. Now, this by itself looks horrible. If you look at the TEM, you would go, how would he ever publish that? He wouldn't. So the trick here is to not leave the templates in. The trick is to take the templates out one at a time. So we've managed to selectively detemplate the macropores using a cold toluene extraction. So we can now empty the macropores whilst the mesopores remain blocked. Why is that useful? It's useful because these macropores can now have their surface functionalized selectively. So we can introduce, for example, an octyl group to make these macropores hydrophobic. We can then take out the template that's inside the with using methanol. We take out the P123, and we now have a completely empty architecture. So we have large macropores, you can see here, a few hundred nanometers, and we have mesopores that are well defined as well, and they're empty. But the surface chemistry is different. The macropores are hydrophobic. The small pores you can see here are hydrophilic. And that means when we put a metal precursor in, they will go to different locations. So a platinum aqueous precursor, for example, will go only into the small pores because they are hydrophilic, whereas a larger nanoparticle of palladium, which has some organic ligands around it to stabilize it, will only go into the hydrophobic cavities, the large pores. So we've managed to achieve selective patterning and compartmentalization of platinum nanoparticles in the small pores and palladium nanoparticles in the big pores. I'll just show you a little animation, makes it easier to understand. So we take our porous architecture, we turn it pink, we hydrophobize the large pores, we put platinum nanoparticles into the small pores, then finally we put larger palladium nanoparticles selectively into the bigger pores. So we've got two types of catalyst site in the same particles, but in separate parts of the pore network. Here is a tomogram showing you the separation. So what you can see here is some very large particles. These are the palladium nanoparticles, and they're only on the surface of the larger pores. And then there's some smaller dots that you can see. These are platinum nanoparticles, which are in the mesopores, the small pores. Easier to see here. So here we've got some rendering of those tomograms. So what we can do is that if we look at just the surface of the macropores, we see only large particles. These are palladium. If we make the surface semi-transparent, you can now start to see these small particles appearing. These are platinum nanoparticles, and you can even see the pore network itself. So these are the mesopore channels that are decorating the outside of a large macropore. So we can see that we have palladium nanoparticles in the large macropores. That's here. We can see smaller platinum nanoparticles just in these mesopores, so in these smaller channels. And we have the ability to image the individual structure. So does the catalyst work? Well, I wouldn't be telling you about it if it didn't. So the first question, though, is how does it compare to, for example, a physical mixture? So if I make a conventional palladium and a conventional platinum catalyst and simply throw them separately into the same flask, we make a physical mixture, and we try this transformation of the alcohol to the aldehyde to the acid. What you find is that the catalysts are very good for the first step of the reaction. We're very good at reacting the alcohol, but we make very little of the final product of the cascade. So that's the acid here. By comparison, the spatial orthogonal catalyst is extremely good at making the acid. It does the cascade. It can do both steps of the reaction. So just to visualize that, the alcohol molecule enters the big pores, undergoes the first transformation to an aldehyde over palladium, diffuses into the smaller pores, where it undergoes a second oxidation step to form the acid. So there we go. We've got a spatial orthogonal catalyst allows us very precise control over the sequence and the communication between these two active sites. Is it possible to achieve the same goals using clever engineering? The answer is yes. I've shown you just now batch reactor results. You can do the same chemistry in flow, in which case you can have a packed bed of just the palladium catalyst, a second packed bed of the platinum catalyst, and you can flow your reactants through. So the alcohol does the aldehyde transformation over the first reaction, and then you have the aldehyde transforming to the acid over the platinum catalyst. And these systems are very stable. So if you look at the batch reactions, your turnover numbers, the activity of the catalyst is quite low versus the flow reaction system. So both these two scenarios, having the catalysts coupled together in the same particle, spatial orthogonal, or put in direct sequence to each other in a flow reactor, allow you to get very high performance for cascade oxidations. We've since moved on to make a acid-base variant of those. So I've talked about metal catalysis. I'm now going to talk about acid-base catalysis. And you can adopt a very similar approach of this templating approach. You can make a material which is an organically templated material. Here we've got the large polystyrene colloidal templates. These are hard, solid templates. Here we've got the red circles are our small templates, our surfactant templates. But this time we've put a metal ion into the surfactant. We've chelated it, bonded it to the surfactant. So even now at the starting stage, we have a metal phase present within these mesopores. We can now extract, just as we did previously, the large polystyrene templates to make an empty macropore. And we can then functionalize that. In this case, we've chosen to functionalize it with a zirconium precursor to make a coating of zirconium hydroxide on the surface of the macropores. So the macropores have a zirconia coating, the mesopores have magnesium inside, and when we actually calcine, we can sulfate and calcine the material. I'll take you to the end step here. What you end up with is macropores that have sulfated zirconia, which is a superacid, that's a superacidic material, only coating the macropores. On inside, in the smaller pores, we now have MgO nanoparticles. And magnesium oxide is a very good solid base. So magnesium oxide behaves a lot like sodium hydroxide, that's a liquid base, and sulfated zirconia behaves a lot like sulfuric acid. So here we've got solid acid and base forms of our traditional mineral acid and bases. How do you know I've made the thing I say I've made? Well, let's look at some TM images first of all. So here you can see the macropores, this large curvature here. That's one section of the macropore. And you can see in between the macropores, we have these mesopore arrays. Each of these holes here is about 5 nanometers across. And it's those that are decorated by magnesium oxide. So if you now do some careful EDAX mapping, so we're now looking at elemental analysis, what you find is that nearly all the magnesium sits inside the mesopores, these small channels, and most of the zirconia is on the outside. It's coating the macropores. So this is a kind of image that we have here. We have a macropore. Now instead of a metal catalyst inside it, we have a thin coating of zirconia. And in the smaller pores, we have magnesium oxide nanoparticles. And it's easy to see by looking at the ratio of our zirconia to magnesium. And what you find is that in the macropore regions, there's a very large amount of zirconia, whereas in the mesopores, there's basically no zirconia, only MgO. So again, we've achieved spatial separation of these two active catalysts, sulfated zirconia and magnesium oxide. So do they work for acid-base cascades? So the answer is yes. We recently published this work. Here's an example of a fine chemical synthesis. So here we're looking at highly functionalized molecules in which we have, first of all, an acetal that we're going to do an acid-catalyzed deacetylization. We're going to break these bonds off and convert our BDMA into benzaldehyde. And then we're going to couple the benzaldehyde with an ethyl cyanoate to make a cyanoate ester. So these are quite high value chemical products here. So step 1 is acid catalyzed, step 2 is base catalyzed. So if we look first of all at the reactivity of our catalyst for step 1, again looking at a conventional catalyst. So this catalyst here is a pure acid catalyst. What you find is that our spatially orthogonal catalyst that has acid and base sites performs very well for the first step. So this is a pure acid catalyst. This is our spatially orthogonal acid base. The two essentially are identical for conversion of this molecule here. However, and in fact, if you look at the final product over here, the yields of BCA are very poor when you use an acid catalyst alone. That's because an acid catalyst gets stuck here. It cannot do this transformation. So step 1 goes very well over our spatially orthogonal catalyst. How about step 2? Let's look at benzaldehyde reacting with this ECA. If you take a solid base catalyst, so pure MgO, just to say this part here is just a silica framework. So here it's magnesium oxide on silica. Here it was sulfated zirconia on silica. So the framework itself is inert. What you find is that we have the MgO catalyst is very active for this step here. And so is our spatially orthogonal catalyst. It's also very active for that step here as well. So our spatially orthogonal catalyst can do both steps, the acid step and the base step. And that's why the overall yield of BCA is about 70%. Is far superior to what you have as you see a physical mixture. So if you just take a physical mixture of a normal solid acid and solid base and put them into the same flask, you get quite poor yields of the final product. Whereas here, bringing these two sites, the acid and base site, close together allows us to do the cascade very effectively. So again, an acid and base reaction there. I'll show you another one so we can achieve more than double the product yield by doing that. Another more important example is one that relates to essentially sustainability and making a biofuel. And there's a lot of waste cooking oils or low-grade oils that are made around the world. They look horrible. They're not the sorts of things that you can put into your cars. And so there's a need to try and transform these into a biofuel. The problem is they look horrible because there's a lot of this impurity called a free fatty acid inside it. Now, traditionally, when you make biodiesel, you take an oil, a bio-oil, and you use a base catalyst to do the transformation. So here's an example of how you make biodiesel normally. You take a pure oil and you transesterify it using an alcohol to make biodiesel and some glycerol. So this is a base catalyzed reaction. And that's a problem because base catalysts don't like acid impurities. If you expose a base catalyst to this used cooking oil, it instantly deactivates the catalyst, it poisons it. So we were trying to work out, could we create a new spatially orthogonal catalyst that could overcome this by including an acid catalyst inside the particle? So acid catalysts are actually really good at removing these free fatty acid impurities. So our idea is that we could make a catalyst that would have essentially two types of active sites inside it. In these big pores, we would have acid catalysts that would allow us to do the free fatty acid impurity removal. So in this pore here, we would do an esterification. We would remove the free fatty acid, and that would allow these green tag molecules to migrate all the way through into the smaller pores where they would find a base catalyst. And the crucial thing essentially is that by removing the free fatty acids in this pore, it means we're protecting the base catalyst from ever being poisoned. That was the theory. So we made a framework, which you can see here, in which we would have essentially esterification going on over acid catalysts in the large pores, and we would have trans-esterification, so the triglyceride turning into doing a trans-esterification in these base catalyzed reactions in the mesopores. So how does the catalyst actually perform? Well, if you look over here at the graph, what you find is that if you feed any of these catalysts pure triglyceride, a pure oil, they all do very well. So a pure base catalyst is okay for making biodiesel as long as you have a pure feedstock. So our spatially orthogonal catalyst performs just as well as a physical mixture or of an acid-base catalyst or a pure base catalyst. However, what happens if we take our pure oil and we throw in a lot of acid impurities that occur in real used waste cooking oils? Well, the answer is that our catalyst is still just as good, no change at all. However, a pure base catalyst is dramatically poisoned. It can no longer perform because these fatty acid impurities neutralize the base. So a physical mixture and a pure base catalyst perform very badly when you have free fatty acid impurities in your feedstock. However, the spatial orthogonal catalyst just keeps on ticking over. It works very well. And I'll just finish by explaining how this is. Why is it that these catalysts, these spatial orthogonal catalysts, work so well? And I'll turn to some NMR. It's a very complicated plot on here, so I'm not expecting everyone to understand it. What we're looking at here is some diffusion NMR of our hierarchically porous catalyst. So we've got big pores and small pores, etc. What we're looking at is trying to understand how molecules move between those different pores. So what you can hopefully see just from the red words here and some of the arrows is that the solid state NMR experiments, solution phase, these are solution phase NMR experiments where we're looking at the movement of the molecules through the pore network. What we can see is that we can detect the presence of molecules moving between big pores and small pores, macropores and micropores. We can see the moving between mesopores, so mid-sized pores, and very small pores, micropores. We can see molecules moving from the liquid phase, this bulk solution, into our large pores, and we can see the movement between macropores and mesopores. Okay, so I've said a lot of words there. What does it mean? It means that our catalyst allows molecules to move from the bulk reaction mixture into the macropores, and from the macropores then into the mesopores. However, we cannot move molecules directly from the bulk reaction mixture into mesopores. Why is that important? It's important because it means that reactant molecules have to go through macropores where our first catalyst site is located before they can move to mesopores where the second catalyst is seated. In other words, we now control the reaction sequence. We can make a molecule find one catalyst active site first to drive a cascade before it finds the second site. Normally, if you put a mixture of catalysts into a beaker, you have no control over the reaction sequence. Reactants will go wherever they like. In our catalysts, we can control the sequence of reactions. That's a powerful thing. So I'm going to finish there by just summarizing. Hopefully, I've shown you that by using this selective detemplation approach, you can make hierarchically porous materials, which is a common, well-known thing, making hierarchically porous materials, but it's not well known that you can actually locate different types of active sites in different parts of the catalyst. So we've shown you spatial separation of distinct active sites, for example, platinum and palladium. And I've shown you that these active sites could actually be active sites that don't like each other. They could be antagonistic, which is the case for an acid and a base. These are active sites that must not meet each other. otherwise they neutralize. And that's been achieved by using this selective detemplation. Normally both templates are taken out together. We've done it one step at a time, and that allows us to put different active sites into different parts of the particle. And that's important because it now gives us very precise control over the sequence of reactions in cascades. I haven't mentioned this, but just to be aware that all of the pore properties, so the pore sizes, the size of the macropores, hundreds of nanometers, mesopores, 5 nanometers, and the way they connect to each other, whether it's 2-dimensional connections or 3-dimensional connections, all of those can be controlled. So we can tune all of the pore structures to make the pores bigger or smaller, etc., to control the size of molecules that can access them. The two examples I've shown you are for a palladium platinum meso-macrosilica, where we drove a reaction, which was a one-pot cascade oxidation, where we took an alcohol, we oxidized that first over palladium to an aldehyde, and then we oxidized the aldehyde over platinum to an acid. And we did that using the metals in 2 different pores. I've also shown you the acid and base approach, where we can do, for example, biofuel synthesis or fine chemistry. And because the pores are so big, so because these macropores are hundreds of nanometers, you can even imagine putting an enzyme in one of the pores and putting a metal or an oxide catalyst into the smaller pores. So you could do tandem chemo-biocatalysis now. So with that, I'll stop and just thank all of my co-workers, particularly Professor Karen Wilson, my colleague for many years here now at RMIT, a group of people who've helped with, for example, the NMR studies, which were conducted at University of Western Australia. We've got collaborators who do a lot of electron microscopy, so Rowan and Paul at Cambridge University. And we also made use of a lot of synchrotron facilities to characterize the active sites. So thank you very much for your attention, and I'll stop there. Thank you.